So this week's tutorial is based on homework number 5, right? So the tutorial question in the solution can be found on your Moodle shop. So let's start with this week's tutorial. There's 2 problems for this week's tutorial, right? So let's start discussing them. Problem number 1, consider a communication system using blocking code. If we wish to transmit blocks of data of length k is equal to 3 bits and width n is equal to 5, right? So what this means is that the transmitting block length is k is equal to 3 bits, right? So basically that means what is the value of this? 2 to the power of 3, since it's given in bits. So this is basically equivalent to 8 code words that is being transmitted in this transmitting block, right? 8 code words are being transmitted, and each code word is made up of 5 bits long. Okay, so rather than telling you that it's 8 code words that is being transmitted, it is just telling you that the transmitting block of data is of length k is equal to 3 bits. It's basically given in number of bits, right? So part A of this particular question, right? Part A of this particular question says find the number of possible words. So the possible words are made up of bits, right? So in this particular case, each code word is made up of n number of bits. So basically, number of code words are given by 2 to the power of n, which is equal to n is equal to 5, right? So 2 to the power of 5 is equal to 32 possible code words that will be transmitted. Now, the next question says how many valid code words are there? So the length or the number of code words that will be transmitted is of size 3 bits. That means basically number of valid code words that will be transmitted is basically equal to 2 to the power of k, which is equal to 2 to the power of 3, which is equal to 8 valid code words. So that means this transmitting block transmits this transmitting block transmits 8 valid code words with each code word made up of 5 bits. Okay, so moving on to question number on problem number 2. For the following primary sequence, for the following binary sequence of D1, D2, D3, D4, right? This is the data sequence that is given to us. A, calculate the Hamming distance between D1 and D2, D1 and D3, D1 and D4, D2 and D3, D2 and D4, D3 and D4, right? So basically what we need to do is find the distance between D1 with D2, D1 with D3, D1 with D4. And since we have already found the distance, I mean, if we compute the distance between D1 and D2, that will be the same distance between D2 and D1, so that we can ignore D1 with D2. And then next is we need to find D2 with D3, D2 with D4, right? Next is D3 with D4 only, because the distance between D2 and D3, either way, if you do it with D2 with D3 and D3 with D2, the distance will remain same, right? It is basically saying that one is, let's say, one set of data is point A, the other set of data is point B. So if you find the distance between A and B, it is going to be, I mean, let's say if the distance between A and B remains, let's say 1 meter, so the distance between B and A will remain same, isn't it? A with B, distance between from A to B is 1 meter. Distance from B to A is also 1 meter, isn't it? So likewise, there is only 1, 2, 3, 4, 5, 6 unique distances, right? That you will be able to compute, right? Like I said, distance from A to B is also equal to distance from B to A, right? Keeping that in mind, if we say that the distance between data points D2 and D1 is same as distance between D1 and D2, right? So basically the distance between, let's say, point X and dy, data point dx and dy is also equal to the distance between dy and dx, okay? So based on this property, we can see that we can find the distance in a matrix form. Let's say we label the columns this side. I mean, this particular row, the top row with one set of data, right? And the other column with another set of data. So basically, we label each of this particular column data D1, D2, D3, D4. The other side D1, D2, D3, D4. You know, like we do the multiplication between two numbers. Same way we can do it in a matrix form. Write the distance between each point, right? So we can write the solution in a matrix form. So let's say this particular part, the top row, each of these is data points 1, data point 2, data point 3, data point 4, right? And this side is data point 1, data point 2, data point 3, data point 4, right? For convenience, it's just written 1, 2, 3, 4, but it should be D1, D2, D3, D4, D1, D2, D3, D4. Okay. Now we have to find the distance between D1 and D2, right? If you go across this column, now we cannot find the distance between D1 and D1, isn't it? So we can just put a dash, right? That's undefined. Then distance between D1, right? This is D1 and D2. Distance between D1 and D2 is oh, sorry, I forgot about the Hamming distance. The Hamming distance is basically the number of bit difference between each of the data set, right? So let's do the first one to show you what exactly what I exactly mean, the number of bit difference, right? So the distance between D1 and D2, right? Distance between D1 and D2 is, like I said, the amount of bit difference. So these two are like bits, so that won't be counted. These two are unlike bits, so that is one difference. These two are unlike bits, so that is the second one. These two are like bits, so we can ignore them. These two are unlike bits, so there's the second difference, third difference. These two are also unlike. So how many unlike bits do we have? Or how many bits in that particular data sequence is different? 1, 2, 3, and 4. So basically we have 4 bit differences between D1 and D2. So the Hamming distance between D1 and D2 is 4, or the Hamming distance between D2 and D1 is also 4, right? Okay, so the Hamming distance between D1 and D2 is 4. Okay, so like I said, the distance between D1 with D2 is also same as the distance between D2 and D1. So basically we can ignore this, right? Or we can also write 4, right? Okay, let me just write 4. Okay, likewise, if you do it for distance between D1 with D3, so you can see D1, this is your D1, this is your D3. So how many bits are different? This one is different, the first bit is different, second bit is also different, third bit is also different, fourth bit is like, fifth bit is like, the last bit is also different. So how many differences we have? 1, 2, 3, 4. Okay, so the distance between D1 and D3 is also 4, right? Okay, so likewise, the distance between D3 and D1 will also be 4, isn't it? We'll see a trend. Just let me complete the first one. The distance between D1 and D4, the distance between D1 and D4 is, again, if you compare the number, the bits, right? These two are like bits, so ignore that. These two are unlike bits, so that is 1. So this two, at this particular bit, there's a difference. 0 and 0 unlike bits. 1 and 1 are like bits, 1 and 1 are like bits, 0, 0 is like bits. So we have only one bit in this particular sequence, in between these two sequence, that is different, right? It is this second bit over here, right? Okay. So what we do is the Hamming distance between D1 and D4 is just 1. You can see that we have 4. So distance between D1 and D4 is 1, right? So what this means is the distance between D4 and D1 is also same, isn't it? So you can see the row over here, this row is the column of this particular part, isn't it? Okay, so that is why we can ignore this, right? Because whatever we have over here, it is similarly reflected over here. Okay, so moving on to the next one, the distance between since we have this one we have completed because the distance will not change whether you do it for if you find the distance between D1 and D2 or the distance between D2 and D1, right? Both are like, right? Both are equal. So you can just fill this whatever data you have in this particular column, in this particular row as column over here, or you can just simply ignore it because this half of the data, this triangular part is enough to tell you that, I mean, this should give you enough information about the distance between the other set of, I mean, the lower end of this particular diagonal. Okay. So if you do similarly to compute the differences between D2 and D3, you'll find the difference is 2. D2 with D4 is 3. D3 with D4 is 3 again. And remember, you cannot find the distance, or the distance between this between the data sets itself is undefined, right? So the distance between D1 with D1 is dash. D2 with D2 is again dash, it's undefined. D3 with D3 is again undefined. D4 with D4 is again undefined or null, right? Right, so whatever data you have, it is reflected over here. So the distance between, you can see again the distance between D2 with D3 is just 2 bits. So again, it will have the same reading for D3 with D2s due to this particular property, right? So this would be 2, and then this would have been D4 with D2 is 3. Okay, and D4 with D4 with D3 is again 3. So you can see in this particular table, whatever data you have, it is directly reflected on this particular end. So it is being mirrored across this diagonal, right? So that is why this particular half, the upper part of this particular diagonal, is sufficient to give you the sufficient information at below. And also this particular question just says find the distance between D1 and D2, D1 and D3, D1 and D4, D2 and D3, D2 and D4, D3 and D4. So whatever the question has asked, we have been able to justify that, right? Or give this particular solution. All the particular values are there. We needed to find 1, 2, 3, 4, 5, 6 values. How many values do we have? 1, 2, 3, 4, 5, 6 values, right? So basically we are able to answer this particular question in this particular way, right? So basically Hamming distance is the number of bit difference between the two sets of data, right? Okay, so here's that. Moving on to the next part of this particular question. Next part of the question says the following bit stream, right? This is the bit stream that is given, contains the data and the FCS. FCS means the frame check sequence, right? Remember we did this last week. So it says, the question says, find the FCS used if the sequence used for coding it was 1000111, right? So this is basically the polynomial that was given or used to find the FCS, right? For a given particular bit stream. So based on this, remember, like I said, the size of the polynomial, right? Based on the size of the polynomial, the FCS will be 1 bit less than the polynomial. So in this particular case, our polynomial is how many bits? So if you count the number of bits in this polynomial, you'll see that the size of this particular polynomial is 7 bits, right? So our FCS will be 1 bit less than this. So basically 1 bit less than this is this will give our FCS length. So our FCS length is basically 7 minus 1, which is equal to 6. Okay, so our FCS is 6 bits long. So what do we do? The FCS is added at the end of this data stream, right? So 6 bits at the end of this particular data stream is my FCS. So extracting these 6 bits from the end of the data set, right? This 6 bits is my FCS, right? So in this particular case, this 6 bits form my FCS, right? You can see this is what has been highlighted over it. So these 6 bits are my FCS. So basically FCS values are 101100. Okay. Moving on to the next part of this particular question. Plot the data using the 8-level PCM scheme with a sampling interval of 1 millisecond and a voltage equivalent of 2 volts per level. So this means there's 8 levels, and each level has 2 volts difference, right, between it, right? Each level is made up of 2 volts, basically, right? So it also says locate your first sample at t is equal to 0 milliseconds and in the middle of the voltage point in the relevant range, right? So based on this, whatever is given here, we have to plot the data for a 8-level PCM. So for a 8-level PCM, how many bits are needed to represent 8-level PCM? 2 to the power of n, which is equal to 8. So basically, we need 3 bits to represent this 8-level PCM, isn't it? Right? Because 2 to the power of 3 will give me 8. So the maximum value that can be represented, right? Remember, a 8-level PCM will start from level 0 and go up till level 7. So likewise, 2 to the power of 3-bit system will also be able to show you a value from 0 till 7, isn't it? So there are 8 different values. So we need 3 bits to represent a 8-level PCM. Okay, so we need a 3-bit system. So what we do is we know that from this previous question, we know that this is my data stream, right? The rest of this last 6 bits are my FCS. So what we do is we group this data, right? Again, we group this data stream into 3 bits, right? So if we do that, we'll find the data stream, right? So what we do is we group this particular data stream into 3-bit each. So if we do that, you can see this is the data stream over here. This is the data stream, right? This is my data stream, and it has been grouped into 3s. And each data stream represents the level at which the signal is represented at, right? So 001 is the digital value, or the decimal value of 001 is 1, right? 101 is the digital value, or the decimal value is 5. 111 is the decimal value of 7, right? It gives a decimal value of 7. Likewise, 110 gives a decimal value of 6, and so forth, right? And each decimal value, right, in this particular case, each decimal value will represent my level, okay? So based on this, right, after grouping the data stream into sets of 3 bits each, we find the decimal values that will represent the level at which the signal is present, right? And based on the question, it says locate your first sample at t is equal to 0 milliseconds. So we have to start at t is equal to 0 milliseconds and plot all these data streams, right? And it says in the middle of the voltage point in the relevant range. So if it falls in range number 1, right, in this particular case, just for sample 0, sample 0 at t is equal to 0, right? So t is equal to 0. It falls in level 1. So level 1 is where? Level 0. Level 1 is in this particular range, isn't it? So it says in the middle of the voltage point. So in the middle of this, the range for this level 1 is from 2 to 4. So in the middle is 3 volt, right? So we'll plot our point at 3. So likewise, if you do for the other points, you'll see that this falls under the level 5 point, right? Again, for the second one, I'll show you for the second one again. Second one falls, the second sample actually the second sample falls under level 5. So level 5 is between 10 and 12, right? 10 and 12. So in the middle, that is 11, right? So there is 11. So voltage value will be 11 that will be represented on the graph, right? So likewise for 7, 6, 0, and 4, we identify where the points will fall into, right? So once we have the voltage value, we can also see that it is sampled at 1 millisecond. So basically, we start at t is equal to 0 milliseconds and plot. So how many points we have? 1, 2, 3, 4, 5, 6. So we just have to plot up till t is equal to 6 milliseconds. Sorry, t is equal to 5 milliseconds, because the initial point is plotted at t is equal to 0 milliseconds, right? So based on this information, what we do is this axis is my time axis, right? This axis is my voltage axis, right? So it says the voltage axis, I'll divide it at, since it says each level, right, a voltage equivalent of 2 volts per level. So 2 volts forms a single level, right? So I'll start from level 0. So 0, the next level will start at at 2 volt, right? So 0, 2, and the next one will start at 4 volts. So that is why I'll divide this axis at intervals of 2 volts each until I'm able to represent 8 level PCM. So 8 level PCM will start at level 0 and go up till level 7. And each level is made up of 2 volt, right? So this particular axis will represent that, right? So based on that, the decimal values of 001 is 1. So it will fall into level 1. So t is equal to 0. You have to start at t is equal to 0 milliseconds. So the first point falls under level 1. So in middle of these two, 2 and 4, that is 3 volt, right? Next one falls under, that is sample number 2, or at t is equal to 1 milliseconds. That is, the value is 5. So the value is 5, so it will fall under level number 5. So under level number 5, if you plot this in between level number 5, that is 11. So the next point will be at 1 millisecond at over here at 11, right? 11 volts. The next one will be at level number 7, right? Level number 7 at t is equal to 3. T is equal to 1 millisecond, right? This is at t is equal to 0. This is 1. This is t is equal to 2 milliseconds. Sorry, at t is equal to 2 milliseconds. Again, this particular value represents level 7, and the voltage value will be 15 volts. It will be plotted. So level 7 falls between 14 and 18. So in between is 15 volts. That is where we plot our points. Likewise, we do it for the others, and we'll get a graph of something like this. The last point is at t is equal to 5, right? T is equal to 5, or t is equal to 5 milliseconds. And the value represented by the last set of bits is 4. So at t is equal to 5 milliseconds, the value falls under level 4. So level 4 is in between 8 and 10. So it says the middle of the voltage point. So the middle of the voltage point is 9, right? So the value will be 9 volts. So that is what this particular voltage has been written over here. So basically, we find this, we convert this, first we group it into the number of bits based on the level of the level of the PCM. So if it's a 8 level PCM, so we need 3 bits to represent 8 level system, isn't it? So we group it into sets of 3. If it was a 16 level system, so we'd have needed 4 bits, right? So group the system into 4 bits, right? So group it into that number of bits, and then find the decimal values, then find the decimal values of each set, right? Like it is done over here, okay? And that decimal value will represent the level, okay? And then you can plot the points at that particular level, right? So the first sample was 001, so it was plotted at level 1. So as per the question, it says we have to plot in the middle of the voltage point. So in the middle of level 1, it was plotted, right, at voltage 3 volt, right? So likewise for the other points at 11, 15, 13, 1, and 9, the other points were plotted. Moving on to part D of this particular question. Part D of this particular question says obtain a new data stream from the previous graph, part C, right, by observing 7 samples at a sampling rate of 0.5 milliseconds. First sample should start where the signal starts. If a sample is in the middle of 2 levels, take the lower level. So we need to take 7 samples. We have to start at t is equal to 0 milliseconds, or the first sample should start where the signal starts. So our signal starts at t is equal to 0 milliseconds, isn't it? So we'll start at t is equal to 0 milliseconds, and it will be sampled at the sampling rate is of 0.5 milliseconds, and we need to take 7 samples. So that means we start at 0, the next will be at 0.5, 1, 1.5, 2, 2.5, and 3. So we have how many samples? 1, 2, 3, 4, 5, 6, 7, right? We have 7 samples. So we have to take the sampling at these intervals, right? In order to extract our 7 voltage levels, right? So going back to the graph, it says the first point is at t is equal to 0. So at t is equal to 0, the voltage reading is 3 volts and it falls in the level 1. So sample voltage is 3 and it falls under level 1. At t is equal to 0.5 over here in between. So if you run a straight line, right, straight line, you can see it will intersect somewhere here, and that will be around 7 volts, right? And it falls in the level 3. So at 0.5, the voltage is 7 and it falls in the level 3. Likewise, you do it for the other voltage points, right? And you'll get a reading of something like this, right? So you'll get a voltage reading for 1 millisecond at 11. It will have a voltage reading of 11, and that will fall under level 5, right? So based on these levels that you will get, right? The other thing, at this 2.5, at level 2.5, right? At t is equal to 2.5 milliseconds, when you are sampling this particular set of data, right? When you're at 2.5, so it will fall between 2 and 3. So if you run a straight line, just run a straight line up over here, you can see that this particular data will fall at 14, and 14 falls like it's at the border of these two, right? Since level 6 starts at 12 volt and goes to 14, and level 7 goes from 14 till 16, so it's in between level 6 and 7, right? Okay, 14 volt is between level 6 and level 7, so it is a borderline case, isn't it? So as per the condition, if a sample is in the middle of two levels, take the lower level. So in this particular case, we'll have to take level 6, right? We have to take this particular point or read this particular point as level number 6. So that is why the reading of this voltage is 14 and it falls in the level 6, right? Okay. So likewise, if you do it for the other times, you'll get something, right? The voltage readings that you'll be getting is this, and the level each of these particular points falls is this, right? Now, like I said, the PCM code, the PCM, these are the PCM, the levels are the PCM values that you get, right? So we have to find a new data stream. So the PCM code that you'll be getting, or the new set of data stream that you'll be getting, is just you need to convert these levels into its binary representation. So the maximum value that of this particular binary, this particular values, the maximum value out of this number of levels is 7. So 7 is basically represented by 3 bits, isn't it? So again, it will be a 3-bit long system. So you'll be writing or representing each decimal values with 3 bits each, right? Just because of this maximum value of 7, 7 value can be represented by a 3-bit system. So all of these decimal values will be converted into binary of 3 bits long, right? So converting 1, right? Converting. So if you just directly write the number of levels, so you write the number of levels over here, and directly transforming each decimal value into its binary representation of 3-bit long, we'll be getting 001. Representation of 3 is 0011. 5 is 101. 6 is 110. And likewise for the other bits, you'll get this particular data stream, which will be the new data stream from the graph, right? So this is the solution for this particular question. Moving on to the last part of this particular question, it says E, find a new FCS for the data obtained in the previous problem using P is equal to 100101, right? So we now, based on this, right, based on our previous question, this is the new data stream that we have, right? So for this particular data stream, this is the polynomial that is given. Now we have to find our FCS for this particular data stream. So as per the rule, remember what I said is the FCS will be 1 bit less than the polynomial itself, right? That will be used to transform the data. So our polynomial is of how many bits long? 1, 2, 3, 4, 5, 6, right? If our polynomial is 6 bits long, our FCS will be 5 bits long, isn't it? Right, so that is what is written over here. So once we find how many bits the FCS will be, right? So let's say in our case, it is 5 bits long. So what we do is the next step is get the data stream with that number of zeros. So if it's 5-bit long, so we add 5, or we paired the data stream with 5 zeros, right? If it was a 6-bit system, I mean, if our FCS was 6 bits long, so we would have paired the data stream with 6 zeros, right? So in this particular case, our FCS is 5 bits long, so we paired this data stream with 5 zeros, right? So we add 5 zeros to it. So this number of zeros will depend on the FCS size, right? Okay. So once we have done that, right? So what we have to do is we have to perform, like, remember last week we performed the arithmetic 2 modulo, right? So arithmetic 2 modulo is basically a XOR operation, isn't it? So what we need to do is we have to perform the XOR operation of this, right, with 6 sets of streams at each time, right? So what we do is we write the data stream with the padded number of zeros, right? We write it down, and then we write our first bit corresponding to the first one from your left, right? First one that we see from your left in this data stream, underneath the first one, we write the corresponding first bit of this polynomial, and the rest of the bits will follow, right? So you can see the first 2 bits are null, right? Or basically 0. So we start at the third bit. So under the third bit, straight under the third bit, we write our polynomial, right? Right, like we did last week. It's the same procedure. Again, we write our ones, and then we perform our XOR operation. Remember, if we have a set of data, I mean, if we have, let's say if we are representing, if we have a binary value of 1, 1, this is also equal to, in 3-bit, as 0, 1, right? By adding an extra 0, the value of this binary digit does not change, isn't it? So that is why we ignore the first zeros that we get, right? So that is why we are ignoring this, right? The same way, as soon as we get zeros in front, we ignore that, right? Or we represent it with dash, right? It does not change the value of the particular binary system. Okay. So continuing with it, right? So once we have written our polynomial, we now have to perform our XOR. Remember, XOR operation, likes will give us 0, unlikes will give us 1. So 1 with 1 is going to give me 0. So I'm going to represent, I'll just write a dash there. 0 with 0 is going to give me 0, so dash. And then once I get my first one, I'll start writing my values, right? So 1 with 0 is going to give me 1. And then 1, 1 is going to give me 0. 1 with 0 is going to give me 1. And 0 with 1 is going to give me 1. So once I stop here, what I do is, how many bits do I have? 1, 2, 3, 4. Start counting from the first one that you have, right? After the XOR operation. So we have 1, 2, 3, 4 bits. So what we do is we carry, since our polynomial is 6 bits long, we carry the 2 bits down, right? 1 and 2 to make it 6 bit long. And then we write our polynomial under the first one, right? Same way. Under the first one, right? We write our polynomial. Again, 1, 0, 0, 1, 0, right? Under this particular bit, we start writing our polynomial. And then we perform our XOR operation again, right? And get the values up till here. So again, you'll be left with 1, 2, 3, 4 bits. And then since we had carried these 2 bits down here, so the next 2 bits that will be carried down in order to make it 6-bit long is 1 and 0, right? So we carry this 1 down and this 0 down in order to make it 6-bit long, and then we write our polynomial 1, 0, 0, 1, 0, 1, right? And then we perform our XOR operation again, and then we carry out the procedure with the other bits, right? You'll be carrying it out until, you'll keep on doing this procedure until your final remainder at each stage, right? The remainder at each stage, like when I mean the remainder, basically this is my remainder, right? At this particular point, whatever result I got, it was 1, 0, 1, 1. So this was my remainder. After carrying these values down, it was made into 6 bits, right? I'll keep on carrying, I'll keep on bringing the bits, sorry about that, sorry. After performing XOR operation, I'll bring this next set of bits down. I'll continue doing it until my last bit, right? And I'll continue doing it as long as my data, the remainder data set after carrying this value down is less than my polynomial size, right? So my resulting value, right? You can see at this particular point, after each stage, right? You are at least getting some values that you are going to bring. You'll continue doing it until the last bit, right? At this particular point, this 0 is yet to come down. The result that you'll be having is 1, 0, 1, right? This is less than the size of my polynomial. However, the remainder value that this 0, after bringing this last bit down, bit down, I'll be only left with 1, 2, 3, 4 bits, right? After bringing my last bit down, I'll be left with 4 bits. After carrying this bit down, after carrying this bit down, we have the number of bits that we are left with. Start counting from the first one, remember, right? 1, 2, 3, 4. We are only having 4 bits after bringing the last bit down. So if we'll stop, right, we cannot perform the XOR operation with the polynomial. So at this particular point, we stop, right? Or the other condition is we'll continue doing this until the last bit, and we'll continue doing it until the last bit, and we'll stop when the size of the polynomial is greater than the remainder, right? This, after each stage, this is my remainder, right? So you can see after the XOR operation, this is my value, and this is after bringing this 0 down, right? I'm only left with 4 values, right? The size of this remainder is 4, right? And this 4, the size of this is 4 bits long. This is less than the polynomial size. So we stop at this particular point. Our FCS is 5 bits long. How many bits do we have? 1, 2, 3, 4 bits, right? Start counting from the first one. So we are left with 4 bits. So in order to make this 4 bits 5 bits long, we just add a 0. It does not change the remainder value, right? So adding an extra 0 in front does not affect the value, so that is fine. So this particular value becomes my FCS, right? So my the remainder value was 1010. Okay, 1010. Just add an extra 0 to make it 5 bits long. So this is my FCS, right? So remember, you start writing your polynomial at the first bit, right? First one that you get, see, you start writing your polynomial. You perform the XOR operation and bring the remainders down, right? At each stage, like you can see at this particular stage, after performing the XOR operation, I was just left with 4 bits. Then I carried 2 bits down to make it 6 bits long, or equal to this polynomial size. So, and in order to perform the XOR operation again, so I'll keep on doing that, bringing down X number of bits down in order to make it 6 bit, right? Keep on adding it until where you reach a point, even after bringing the last bit down, the remainder that you have is less than the polynomial size. At that particular point, you cannot perform the XOR operation, right? If you bring this XOR operation, this last 0 down, and if you see that the value is 6 bits long, right? Since our polynomial is 6 bits long, after bringing this last 0, you are left with 6 bits again. You have to perform the XOR operation with it. In this particular case, after bringing the last bit down, you are just left with 4 bits, right? You don't have any extra bits left. You have brought the last bit down, so you are left with 4 bits. So we stop at this particular place. So we are left with 1010 value, right? We can ignore the first this particular 2 zeros. So this is the value, and then our FCS has to be 5 bits long. That is why we add an extra 0. It does not affect the value, remember? So adding an extra 0 does not change the value that we are left with, right? So we just add in 0 to make it 5 bits long. So that forms my FCS, right? Okay, so we'll stop here. And I'll take your queries, right? So I'll stop recording here, and then I'll take your queries after this.